Hi everyone, it is a continuation of solid state chemistry classes. In this video, we shall learn about the meaning of Bragg's law, Bragg's equation, the derivation of Bragg's equation, and we shall learn how to calculate the interplanar distance by using the Miller indices values of a particular plane in a crystal. Before going to the video, if you have not yet subscribed to my channel, please do subscribe to my channel and press the bell icon so that you will get the notification for any latest update in the channel. Now we shall directly enter into the topic. Let me say, when you pass an ordinary light onto a crystal, obviously you will observe the reflection of the light. The ordinary light can be passed at whatever the angle, and the reflected rays from the crystal can be detected by using a detector in an easier way by keeping the detector at some optimum position or at anywhere. But instead of ordinary light, when you are passing the X-rays, the beam of X-rays onto the crystal, again the reflection will occur. But the reflection of X-rays can take place only at certain angles, then only the detection of the reflected rays is possible. That means, in order to detect the reflected rays from the crystal, in strictly speaking, in order to detect the reflected X-rays from a crystal, the detector is supposed to be placed at a particular angle. That means the X-rays are supposed to be passed at a certain angle from the source onto the crystal surface. So simply we can say the reflection of the X-rays can take place only at certain angle. That is, reflection of X-rays can take place only at certain angle. Only at certain angle. So it cannot occur at all the angles. So the angle at which the incident beam is passing or striking the surface, and the corresponding angle at corresponding angle the X-rays will reflect. So that angle about which we are passing the X-rays onto the crystal and the angle at which the X-rays are got reflected, that angle is called glancing angle. Glancing angle, simply taken as theta. So you define the term glancing angle. It is the angle between the incident beam, or you can take the reflected beam. It is the angle between the incident beam or reflected beam and the surface upon which or from X-rays or incident are reflected. That means it is simply the angle between the incident beam and the surface upon which the X-rays are incident, or it is the angle between the reflected beam and the surface from which the X-rays are got reflected. That angle is simply called as glancing angle. And the determination of this glancing angle can be done by knowing the wavelength of the X-rays and the distance between the planes in the crystal. I repeat, the glancing angle for the X-rays can be determined by knowing the wavelength of the X-rays we are passing and the distance between the planes in a crystal, that what we also called as interplanar distance. So in order to understand the glancing angle, the interplanar distance and the wavelength of the X-rays used for the process of diffraction, Bragg has developed a fundamental equation that gives a relation between wavelength of the X-rays, interplanar distance in the crystal, as well as the angle of reflection, that what's simply called as glancing angle, and that is simply called as Bragg's equation. And that Bragg's equation is simply nothing but n lambda is equals to 2d sine theta. This is called as Bragg's equation. Bragg's equation. And here lambda is the wavelength of the X-rays used, d is the interplanar distance, and n is order of X-ray diffraction. It may be first order, second order, or third order, whatever it may be, and theta is glancing angle. And now we shall go with the simplest derivation of this Bragg's equation. We shall directly enter into the derivation of Bragg's equation. Here, this is the figure which shows the X-ray diffraction by a crystal, and here you can observe we have the several horizontal lines, and this horizontal lines corresponds to layers in the crystal structure, and these layers are separated from one another by equal distance, which is given with the notation d, where d is called as interplanar distance. And when a beam of X-rays is passed on to the crystal, some of the rays will get reflect from the upper surface, and some rays will get absorbed by the crystal and get reflect from the successive layers. And here you can observe PO is the incident light, incident X-ray, which is reflected from the upper layer, that is OP prime, and QB is absorbed by the crystal layer till the second layer, and it got reflected from the second layer, and this R and R dash is the, or else the NR dash is the X-ray which is reflected from the third layer. So this we can easily observe how the X-rays are getting reflected, whether it is from the upper surface or from the lower layers. And if you consider the waves of this reflected rays that is coming out of from the different planes or different layers, the waves of this reflected X-rays will be in phase with one another if the difference in path length of the waves, that mean here you can observe POP prime compared to this QB Q prime is traveled a bit more length in a crystal, so that we can see over here this PO line has been extended up to the second line to the point C. This OP prime is extended up to the line QB up to the point A. So this OA is parallel to BC and this OC is parallel to AB. So that AB and BC, this much is the total path difference between POP prime and QB Q prime lines. And let us come back. The path length, that is the difference in path length of the waves of the reflected rays from the successive planes will be always equal to the integral multiple of the wavelength. So that we can write in this way: the difference in path length, difference in path length, that's nothing but path difference. Difference in path length of waves reflected, that's of the X-rays, waves reflected from successive layers. Successive layers, or you can say it is successive planes, is always equal to the integral multiple of wavelength of the X-rays used. integral multiple of wavelength of X-ray. So this is the condition considered by Bragg. And here, let us now begin the derivation of this Bragg's equation. Here we have totally three triangles, that is OAB and OBC. So totally we are having two triangles. So let us consider both the triangles OAB and OBC. Okay, so from the triangle OAB, for this triangle, here you can observe, for this triangle shall go with sine theta. So for triangle OAB, for this triangle, we know that sine theta is simply nothing but opposite by hypotenuse. So here this is the angle, opposite is AB and hypotenuse is OB. Right. So opposite is AB and hypotenuse is OB. So that's why sine theta is equals to AB by OB. But here OB, this is nothing but D. So AB by D, or else we can simply write AB is equals to, D can be cross multiplied. So AB is equals to D sine theta. And now we shall consider the second triangle present over here, that is OBC. So from the triangle OBC, again we shall go with the sine theta. And here for the triangle OBC, opposite is BC and hypotenuse is again OB. So sine theta is equals to BC by OB. And again we know that OB is nothing but D. So BC by D, that finally we can say BC is equals to, D can be cross multiplied so as to get D sine theta. Okay, and here just now we said the difference in path length of the waves reflected from successive planes is equal to the integral multiple of wavelength. Right, so just remember this one. So therefore the path difference between the first two rays, that is POP prime and QBQ prime, the path difference will be, so here I said the path difference is AB and BC. Right, so path difference, the total path difference will be equals to AB plus BC. This is the total path difference. But we have the values for AB and BC. AB is equals to D sine theta and BC is equals to D sine theta. So as a whole, we can write AB plus BC, collectively we can write 2D sine theta. Right. But when we said that the difference in path length, that is path difference, the difference in path length of waves reflected from successive planes is equals to integral multiple of wavelength of X-ray. So the path difference can be written as integral multiple n of its wavelength, that is n lambda. So this is the Bragg's equation, that what we already said in the beginning. And here we shall say, here the lambda is wavelength of X-ray used, wavelength of the X-ray, and D is the path difference. D is path difference. Theta is a glancing angle or the angle of diffraction, glancing angle. And here N is the order of diffraction. Order of diffraction. And the value of N can be, it may be first order, it may be second order, or it may be third order. And that's details of complete derivation of Bragg's equation. And this Bragg's equation have multiple applications in calculating the interplanar distance, the angle at which we are supposed to place the source as well as detector so as to analyze the complete structure of a crystal, and that what we call as X-ray diffraction studies. So this Bragg's equation is very much helpful in complete analysis the structure of a crystal through the method called as X-ray diffraction studies. And now we shall see by using the Miller indices. So by using this Bragg's equation also we can calculate the interplanar distance, that is interplanar distance. So by using this Bragg's equation also we can calculate the interplanar distance. So apart from this, if you know the value of Miller indices of the plane in a crystal structure, then by knowing the Miller indices also it is possible to calculate the interplanar distance of a crystal. It may be a cubic, hexagonal, orthorhombic, monoclinic, whatever it may be. By using the Miller indices of that particular crystal system, we can easily calculate the interplanar distance. And now we shall see how we can calculate the interplanar distance by using Miller indices. So now we shall see how to calculate the interplanar distance by using Miller indices. So in our last video, we said how to indicate the Miller indices. So Miller indices will be indicating by mentioning the plane orientation with a small parenthesis, and here the values what we used to write within the parenthesis will be mentioned as HKL values. This is the orientation of the plane along x-axis, this is along y-axis, and this is along z-axis. So this is the Miller indices will be called as HKL values. And if you come with a cubic system, in case of cubic system, we know that the edge lengths, that is length of the edge along each Cartesian coordinate, that what we indicate as A along x-axis, B along y-axis, and C along z-axis. In case of cubic system, we know that A is equals to B and B is equals to C. So because of this particular condition, the interplanar distance of the plane, that is DHKL, the interplanar distance of the plane in case of cubic system will be calculated as by using the simple formula DHKL is equals to A divided by square root of H square plus K square plus L square. So by using this formula, we can calculate the interplanar distance in case of cubic system. But if you come to the case of tetragonal system, and we know that in case of tetragonal system, A is equals to B, but that's not equals to C, right? And that's why the value of interplanar distance can be calculated by using a simplest formula DHKL square is equals to A square by H square plus K square, and C is not equals to A and B, right? So that's why, so C square by L square. By using this formula, we can calculate the interplanar distance. And at last, if you come to the case of orthorhombic, in case of orthorhombic crystal system, we know that A is not equals to B, B is not equals to C. And that's why, since none of the edge length are equal to one another, the interplanar distance will be calculated as A by H whole square plus B by K whole square plus C by L whole square. So this is the formula we can use in case of orthorhombic system. Okay, so the formula what we use for cubic system can be applied for the same rhombohedral, and in case of tetragonal we can use the same formula for hexagonal, and in case of orthorhombic, whatever the formula we are using, the same condition can be used for triclinic as well as for monoclinic systems also. So this is the way we can calculate the interplanar distance by using Miller indices. And now we shall solve some of the problems for determining the glancing angle, interplanar distance, and wavelength of the X-rays supposed to be used by using the Bragg's equation as well as based on this particular formulas. Now the second problem is, the problem says calculate the angle. That means we are supposed to calculate the glancing angle, that is theta, at which the second order reflection, that is n is equals to 2, will occur in the X-ray spectrometer when X-rays of wavelength, that is lambda is equals to 1.54 angstrom, are diffracted by the atoms of a crystal, given that the interplanar distance, that is d is equals to 4.04 angstrom. This is also two direct problem, and now we shall see the solution of this one. The formula we can use is n lambda is equals to 2d sine theta, and here we are supposed to calculate the value of theta. So we can modify the formula. Sine theta is equals to n lambda by 2d. So the order is 2 and the wavelength is 1.54 angstrom, that is 10 to the power of minus 10, divided by 2 into interplanar distance is 4.04 angstrom, that is 10 to the power of minus 10. So 1.54 divided by 4.04. Therefore, the answer of this particular problem will comes as sine theta is equals to 0.3812. Since we need the value of glancing angle, that is theta is equals to, sine will comes to the right hand side, so it will become sine inverse. So sine inverse of 0.3812 and the angle is 22.41 degree. This is the answer of this problem. Now, the problem number 3. This is of somewhat different kind of problem. Lithium fluoride crystallizes in cubic system with an edge length of, so edge length is given, that is A. Since we are telling cubic system for which A is equals to B is equals to C. So here we have the edge length value, that is 403.35 picometer, and the plane is given, that is 111 plane. The first order reflection, that is n is equals to 1 in the X-ray diffraction from lithium fluoride occurs at 8.44 minute, 8 degree 44 minutes. Determine the wavelength of the X-ray used. So here the problem is somewhat different. So here the thing asked calculate the wavelength. So that means we are supposed to calculate the value of wavelength. So the formula we are having is n lambda is equals to 2d sine theta. So n value is given, that is 1. Lambda value is supposed to be calculated. Theta value is given, but we don't have the value of d. Interplanar distance is not given. Instead of that, the plane is given, that is 111. So by using this Miller indices, we can calculate the value of the interplanar distance, it is DHKL, since the material is crystallizing in cubic system. So for cubic system, the interplanar distance, that is DHKL, is equals to square root of A by H square plus K square plus L square. Right. And here the value of A is 403.35 picometers, that is 10 to the power of minus 12, whole divided by square root of 1 square plus 1 square plus 1 square, that is H is 1, K is 1, L is 1. So that leads to 403.35 picometer, square root of 1 plus 1 plus 1 root 3. The value of root 3 is 1.732. And dividing this, the value of interplanar distance will comes equals to 232.88 picometers. So we got the value of interplanar distance. And here we can easily calculate the value of lambda. But here the theta value is given in terms of 8 degree 44 minutes, that we can directly convert into degrees, like so 44 divided by, this is the 44 minute, divided by 60, you will be getting 0.73 degree. So wavelength lambda is equals to 2d sine theta whole divided by n, and the value of n is 1. So now 2 into the value of d is 232.88 into sine 8.73 degree whole divided by 1. On calculation, the final value of this thing will comes to be 70.69 into 10 to the power of minus 12 meters. That's nothing but lambda is equals to 70.69 picometers. So here this one is to be multiplied with 10 to the power of minus 12. So this is the final value. So in this way, we can calculate the value of wavelength, and you can calculate the value of glancing angle as well as the interplanar distance by using the Miller indices.